has the... Yes, here it is, and the stage is yours.
Thank you. Good afternoon, dear colleagues. My name is Aleksandra. Today I would like to present to you the work which we are doing in St. Petersburg State University under the head of Professor Grekov. So we will investigate the stress field around cylindrical pore by various surface elasticity models. The outline of my presentation is following. First of all, we will speak about our motivation to solve this problem and make introduction. Discuss various surface elasticity model and difference between each other. Make a general formulation of the problem. I will present you a short plan how to get analytical solution of it. And finally, present explicit relations for the components of stress tensor and make field analysis. Some conclusions and our future work in this area. So many theoretical and experimental works show us that nanoscale grooves and cracks like appear on the free surface at the stage of fabric or after some thermal or chemical processing. Previous talk was where we can find this nano defects, for example. It can be some maybe implantology, for example, because this surface properties are similar to biological sickness, so they have good agreement and integrated in it. For us, the material properties are determined by its chemical composition and structure, and the study of surface phenomena is of great interest because it gives us the opportunity to obtain information about the physical and mechanical behavior for the raw material. So if we go back to the history, the basic concepts of surface interface free energy and surface interface stresses were first formulated by Gibbs. Gerton and Murdoch elaborate the mathematical framework, incorporated these surface stresses in continuum mechanics. Miller and Cheney confirmed this theory with the help of molecular dynamic simulation. Also, you can see on the slide many others who use Gerton-Murdoch surface elasticity theory to solve the various problems of elasticity theory. For example, our scientific group also used this simplification of this theoretical surface model, and we have the results for group 2D problems with nano defects such as holes or inclusions with an arbitrary boundary. So, the most popular and widely used Gerton-Murdoch constitutive equation of the surface is linearized by Formula 1. So here we can see that sigma s is the Pio-Kirchhoff surface stress tensor, and ES is the surface strain tensor. Also for us important to know about these constants sigma 0s. It corresponds to the residual surface stress. And lambda s and mu s surface elasticity constants, which are similar to the Lamé constants for the bulk material. If we speak about simplified Gerton-Murdoch surface elasticity models, we can see these 5 models. So if we go back to this, you can see these 4 terms. For the first simplification, it made by Blinovsky, in this constitutive equation of surface linear elasticity we will present in form 2. So we can see that residual surface stress is appear only in first term. In all other terms, it's equal to 0. So it's first one simplification. Second one, when we take that the surface energy equal to the surface tension. So we have only first term of this equation. Yep, this one. The third one, when we neglecting of the surface elasticity properties. So we take into account that parameters mu s and lambda s equal to 0. Next one is the most useful model. Here we neglected of the surface tensions. There are a lot examples in literature for many others. Another one also, so the fifth and the second models are the most popular in literature. In the second model, in the sixth model, we neglected the gradient tensor. For example, works of Professor Gutkin group. So, if we make the problem formulation, we consider the matrix material, which is homogeneous, isotropic, linearly elastic, and the constitutive equation formulated by Hooke's law. Also, we used the generalized Laplace-Young law in the form 8. So, we consider the problem in the case of plane strain for a circle hole in the radius A in the elastic plane of complex variable. Thus, conditions at infinity are given by formulas 9. To solve the problem, we use relations between components of stress tensor and strain tensor by formulas 10. And all equations for these surface models combined by formulas 11. For us, it's more important these components PS and MS, which have different values depending on all types of this model. So if we change these parameters, we can calculate all these simplifications. So, according to Grekov, the boundary equation has, in the general case, has this form. Here, zeta is the point on the boundary of the circle. A is the radius of this circle. And we have this function Q, which depend on unknown displacement, a vector of displacement. So, for example, in the original full Gerten-Murdoch model, function Qs will presented by formulas 14. Also, when we changed parameters PS and MS, we can present all other simplification models. Which is the main idea how to calculate, how to find the analytical solution. We have two main steps. First of them is to find function Q depending on unknown complex displacement. How to do it? We calculate complex potentials in terms of Cauchy type integrals, and finally we can explicitly solve the boundary integral equation. So complex potentials find by these formulas, and boundary integral equation is formula 16. Here we goes to non-dimensional form and take this our point on the boundary to the unit circle. Also function Q changed to the function f on the unit circle 1. To find the solution of this integral equation, we present all functions here in power series with unknown coefficients, and we can combine them with equal powers and find the solution. So we find this function v. It's equal to displacement u on the unit circle, and after them find the function q. So the final formulas in explicit form to find components of stress tensor is following. And our results, numerical results presented here. So for the numerical results, we used properties of aluminium with orientation 111. Surface parameters were chosen from the work of Miller and Cheney. Surface residual stress from the work done in Japaxen, and elastic constant stakes for the aluminium. So if we are looking on this figure, the distribution of hoop stresses at the boundary of the circle hole, radius 2 nanometers, we can see all these 6 models that I present at the beginning. So this black curve, it corresponds to the full Gertin-Murdoch model. What we can see here that the quantitative behavior of all these curves is in a good agreement, but we have this difference between the full model and fifth model, where we didn't take into account residual surface stress. So how you remember, this is the most popular model in literature. If we are looking to the distribution of normal and tangential stresses, we have another picture. So here, this one is for the fifth model, and also we have this difference for the third and fourth model. This is also black curve is correspond to the full model. So we can see this that fifth model also different for it, and difference between third and fourth. In third model, we didn't take into account surface elasticity constants, mu s and lambda s equal to 0. And for fourth, we also make one simplification with a gradient tensor. So, and here, the biggest difference between third and fourth models, because for the tangential stresses, they are equal to 0. Next slides present the stress components distribution due to angle equal to 0 and 90 degree for all components. Also, we have this different but quantitative agreement. Next one for the hoop stresses, distribution of hoop stresses. And the last results present us size effect, which is show us this nanomaterial properties that what we can see. For the smaller radius of the our circle, we have a so big difference between fifth model and full model. But when we are going to a radius up bigger than 15 nanometers, they are in a good agreement. And when we are going to macro level, we have classical solution for the Kirsch problem. And also similar results for the maximum hoop stresses. Also, we can see the size effect and difference between third, fourth, and fifth models. So, as to make conclusions, by comparing the numerical results of Gertin-Murdoch full model, number 1, with the corresponding results of other model, we can observe that second and sixth yields practically the same, but we have the main, the model 5 not allowing to surface tension gamma 0s, show us the great deviation from the full model, especially for the normal stresses. And for the third and fourth model, we also have display the close results and the great deviation from the full model. In the rest cases, the model 4 does not differ significant from the full Gertin-Murdoch model, and the model 3 consistent virtually with the full model of Gertin-Murdoch. So, all these models are used in literature for some others, and all of them can be useful. But for the different types of size of the effects and for the different types of boundaries, if we calculate some results with finite element methods and have good agreement with this 5's model, but how we know this have a big difference between full model of Gerten-Murdoch. But we have quantitative agreement. So in future we plan to make similar analysis for the more complex defects and also analyze how it will be works for the inclusion, non-inclusion. Thank you for your attention.